All right, let's get started. Okay, great. So today we're going to be talking about evaluation of these big models that we've been discussing for the past couple of weeks. We have primarily focused on text generation problems. As we mentioned when we were covering T5, a lot of NLP problems can be reduced to instances of text generation problems. Here today we'll specifically be looking at evaluations for machine translation, text summarization, and then at the end some human evaluations for more open-ended text generation problems. Of course, we've already seen, like with tasks like sentiment analysis, it's very easy to evaluate these based on things like accuracy, right? And other tasks can be evaluated with things like F-score. But for some of the tasks that we'll discuss today, there are no simple automatic metrics that capture how well a model is doing on this task. And so that motivates a lot of this lecture today. Okay, so before we get started, someone had asked for practical tips on fine-tuning, say, a BERT model or a Roberta model. One of the TAs, too, just posted on Piazza a bunch of tips. He's an expert on this stuff, so if you have any questions, just ask in that thread about how you can make your models perform better or be more efficient or whatever. It should be pretty useful for the homework question as well, which requires you to train or fine-tune one of these models on your data set. Okay, so the midterm date, we already talked about this. It'll be available November 9th. You will have 48 hours to complete it. Today I released a bunch of the previous year's midterms. They're in Piazza, so you can check those out. I'll release the answers to these midterms maybe in about a week or two, so you can take some time to try out the problems on your own, and then you can see how you did. Note that a lot of the questions, especially on the older midterms, like from 2018, are not really relevant to this class. We haven't talked about more classical NLP models or even tasks. And so if you see something that you have no idea what's going on, it's probably because I didn't talk about it, so you can safely ignore it. If you're confused on whether a particular problem can be asked on this year's exam, feel free to put it in the anonymous form or ask on Piazza or whatever. We're happy to. But you should note that the most recent exam, which is the fall 2020 version of this class, I think all of those questions are fair game for this year's midterm. So you should pay close attention to that one of all the ones that were released. All right, what else? So yes, your homework 1 was released. There will also be an extra credit homework, and we're just gonna have it due the last day of class, so whenever your final projects are due. It is quite extensive, so we'll release it probably at the end of the week. You might want to budget more than like a day for doing it. And also, the reason why we're doing this is because some of the coding cells in that homework could be very useful for your final projects. It involves not only like learning from limited labeled data, but also data augmentation techniques, using things like back translation, which we'll talk about later in the semester, to make your models better and so on. So it was a pretty fun homework last year, and we decided to, instead of obligating you to do it, you can do it if you want some extra free points, but should be useful nonetheless. All right, any questions about any of this stuff? Okay. So far, we've talked a lot about these neural language models, right? And the only evaluation metric to say, how good is this language model compared to this other language model, the only metric we've talked about for comparing these models is perplexity, right? We went over perplexity is just a function of the probability that a language model assigns to some held out data. But when we get into more specific downstream tasks, so remember, language modeling is a very, very general, high-level task. It has commonalities with a bunch of different tasks, downstream tasks that we actually care about. But each of these individual tasks has its own nuances, right? So for example, if I'm interested in building a machine translation model, we'll talk a lot more about these models on Wednesday. I'm specifically interested in if I decode an example from my model, like an example translation, how good is that translation compared to, say, a reference translation, right? And so Perplexity does not capture these fine-grained nuances of, you know, I want my translation to be grammatical, I want it to have the same meaning as the original sentence. I might want a more fine-grained evaluation, right? And I might want something that operates directly on the text that the model produces rather than on the probability distribution that it produces. Because, you know, we talked about the sampling-based methods for generating text, or beam search or greedy search. All of these things have a big impact on the quality of, say, a translation as well. Okay, so today we'll start with a focus on machine translation, because that is basically the original text generation task. It's also the most well-defined, probably, although even it is not you know, completely well specified, and that motivates a lot of the design choices made in the various evaluation metrics that we'll talk about today. So for machine translation, the metric that has been used widely for, I don't know how long, maybe like 15-ish years, is the BLEU score. So we'll describe that. The ROUGE score is very similar in principle, but it's applied for text summarization. There's one key difference between those two that we'll cover. And nowadays, there have been some improvements and new evaluation metrics for text generation that are based on these large-scale language models that we've talked about. So specifically integrating things like BERT and ROBERTA into an evaluation metric that works better than BLEU or ROUGE in some cases. And then finally, we'll talk about human evaluation. So what do you do if none of these automatic metrics are expressive enough or meaningful enough to evaluate a particular task? Okay, so these slides were actually made quite a few years ago. I assume Chinese to English translation has gotten better since then. But you know, if you take some translation model, its input is obviously text in some language, and the output is text in a different language, right? And your goal is to see how well the translation system did. In this case, I mean, I don't speak Chinese, but if you just read this English text, it's not great, right? It has a lot of weird artifacts, like what does it mean to solve the basic black and black water? There we have some repetition. There's some black and white water, 2082. Obviously, it's getting these numbers, right? But I'm not sure about anything else, really. So this is one of the issues with, you know, different languages are harder to translate than others, especially if the two source and target languages are very different. French to English is much, much better than Chinese to English. I don't speak French either, so I can't vouch for this translation, but if you just read the English text, it's much more grammatical and seems to make sense, it's coherent. But it would be great if we had a reference translation to which we could compare this to, and then we would know for sure, even if we don't speak French, right, how well our model has done. So machine translation has evolved a lot over the past few years, and on Wednesday we'll see like the current state of the art and what kinds of models are being used these days. But you know, machine translation is not perfect. And even if you're using Google Translate, which has probably the best machine translation models out there, you know, Google has a lot of large-scale proprietary data that they can use to train these models. And of course, they have enough compute to train really, really big models. Still, it's not great for many languages, especially low-resource languages. So the use cases of machine translation are different depending on how good the translation quality is. So for example, if you just want to know the content of some text in a language you don't understand, you might be much more tolerant of things like grammatical errors or even like local inconsistencies. if you can somehow get the gist of what was being said, right? So this used to be the focus of majority of research. Now I think things have improved to a point where we can focus more on settings where users are not tolerant as much of these errors. So for example, if you are talking to someone who doesn't, and you don't speak the same language, you could imagine a real-time translation system that simultaneously translates what you're saying into the language of the other person, so you can have a normal conversation with no lag on either of your parts, but a translation system is facilitating this communication. So this has its a whole nother set of issues, like you need to prioritize the latency of the system as well as the quality. There's a whole subfield of machine translation devoted to simultaneous translation. And finally, the highest quality required is, say I have, for example, a novel that is written in a different language, and there's no human translation of that novel available. It would be awesome if there could be an automatic translation system that could produce high quality text that gives me not only the content, but also the intended author's stylistic decisions, the themes, the other stuff that people read novels for. So one interesting thing about this is that there is a huge community out there for that automatically translates novels written in Chinese and Korean and Japanese. There's these web novels that are really popular, and there's so much content. There are not enough human translators, so a lot of people on like these subreddits and forums will just dump the entire web novel in Chinese into Google Translate, get an output, and then go to these subreddits and complain about how bad it is. But really, they can understand the plot to some extent, but these models make a lot of errors, so it's not very enjoyable to read these translated versions compared to a human translation. So like, if you wanted to solve this problem, you would need an incredibly high quality translation system that made very few errors, preserved the author's stylistic and semantic intent, and so on. Okay, so one of the issues with translation, and really with all text generation problems, is that there's no single right answer. So in sentiment analysis, for example, we know on average that something will be positive, negative, or neutral. It's usually very clear what it is. And there's only like 3 categories that we are interested in. But in text generation, we have a model that is producing a sequence of words in the vocabulary. Our vocabulary could have hundreds of thousands of types in it. It becomes very unclear, like, what does it mean to have a single best translation, right? So in this case, all of these blue sentences here are kind of paraphrases of each other. There are different ways of saying Israeli officials are responsible for airport security. Some of these might be written in a passive voice or use different constructions, but they're basically all saying the same thing, roughly. And what does it mean for one of these to be better than any of the other ones, right? That it's very hard to tell. So this is one of the issues, right? If, for example, we treat this like an accuracy-based computation, where we say this first sentence here, Israeli officials are responsible for airport security, is the only right answer, the only sequence that is correct here. If my machine translation model produces any other sequence, it's wrong, and if it produces this one, it's right. But this is obviously way too harsh, right? If my machine translation model produced the second translation here, it would get 0 points. So we certainly want to assign partial credit or even full credit for these cases where the model has produced, like a paraphrase of the reference that you have, or maybe it gets almost all of it right but misses one thing. That shouldn't be counted as completely wrong, right? So these are the kinds of challenges we encounter with evaluating text generation problems. So, of course, we have many different translations, and one way you could think about doing this is through human evaluations, right? So you can get someone who knows both languages, who's fluent in both languages, and can evaluate how close the machine-generated translation is to the reference translation, or to what should be the correct translation. So in human judgments, there's generally two things that we care about in translation. There's the adequacy, which is how well does a translation preserve the meaning of the source language sentence? And then there's fluency, how grammatical it basically is the output translation. So one way you could think about doing this, if you were to just show these to some bilingual speakers or expert translators, is you can set up a scale from 1 to 5, rate each of these two attributes given the source sentence and the machine translation version. So this has been done and is done a lot. We have these human ratings, and what an interface could look like this, where they have to mark from 1 to 5, is something adequate or is it fluent? So why don't we try this, just to show some of the potential issues. In this case, we'll look at the reference here, so you don't have to know French, but the reference is there not an element of hypocrisy on your part? So we have 3 systems, and we're trying to rate them for adequacy and fluency. So let's do system 1. Would it not as a wave of hypocrisy on your part? So how many of you would rate this 1 out of 5, which is the lowest score for adequacy, given the reference as the... Okay, what about 2 out of 5? Oh, raise your hand, yeah. Okay, some of you. 3 out of 5? 4 out of 5? 5 out of 5? Okay, so between 2 and 4, most of you were around 3. Well, let's do fluency. So how many of you would rate this 1 out of 5 based on fluency? Again, 1 is the worst, least grammatical. Okay, some of you. What about 2 out of 5? All right, 3 out of 5? Okay, 4 out of 5? Okay, I assume no one's at 5 out of 5. So clearly, like, there was some general agreement, like most of you were around 2 or 3 fluency and 3 to 4 adequacy, but this is subjective, right? It depends on what you think a 1 out of 5 means and what you think a 5 out of 5 means. And if you give no training to the people doing this task, like you all had no training, right? Then it's very difficult to make these kinds of judgments. So I'll just skip over systems 2 and 3. TLDR, they're not good either. All right, so that was one issue. What are some other issues of doing this human evaluation that you can think of? Yeah, so it's definitely expensive, right? I might have to hire professional translators or bilingual people, pay them a reasonable wage, right, hourly wage. And there's a cognitive load on their part too. They're not going to be able to just rate millions of outputs from your model, right? So I'm limited in scale, financially and time-wise, how many things I can get evaluated from my system. What are some other issues?
So generally the disagreements are resolved using discussions in these types of evaluation, and that is like how it will be settled might be based on experience. Like someone who has less experience might like agree to the one with more experience, and the point.
So it's an interesting point that you bring up. Like, these things could be resolved through mediation and discussions. Like if 3 annotators disagree on the fluency score, right? In general, they're not resolved at all, though. They're completely separate annotators. They don't know each other's decisions, and they each might annotate, 1,000 or 2,000 outputs, and you, as a designer of the system, will aggregate their responses together. You might measure which examples had a lot of agreement or disagreement, and then make some conclusions about how those were hard to rate. But in other applications, it is kind of more common to have these discussion settings. But of course, having a discussion between your raters makes it even more expensive, right? Now you have to pay for their time to do this, and Yeah, in general, like this is a hassle, right? It costs a lot, takes a lot of time. Yeah.
It depends on individual human opinion. So there could be experts in many fields, but even an expert, like two of them could have different opinions on what is fluent and what's not.
Yeah, I mean, this boils down to the subjectivity of this task or any sort of rating task that requires you to choose like from 1 to 5.
Your annotators might not be familiar with the content of the sentences. Like you need some sort of knowledge to understand something.
Yeah, so this is a big problem for machine translation in particular, where all of the model, even Google Translate, is a sentence level model. So if you put in a paragraph, it's going to translate each sentence independently of all of the other sentences. And in some cases, you might need the surrounding context to make an accurate decision on what the translation is. So there could be missing information.
So in this exercise, it's difficult how to backpropagate. For example, so if we have to use this as training data, what objective we should use is not clear. So for example, if humans are rating this in terms of adequacy and fluency, we need to define we need to have like an objective function through which we can backpropagate so that our model can actually.
So the stuff I'm discussing now is you've already trained your system using the maximum likelihood objective on some training data. Now you're evaluating it on the held out data. We will see later on in this lecture how you can collect judgments from an existing machine translation model and then train another model to predict those judgments. So sort of taking the place of the of the humans in this rating. And this does fairly decently, although not an adequate substitute for the human evaluation. But yeah, if you wanted to talk about using these kinds of evaluations to fine-tune your model to make it a better translation system, that's a whole nother topic which we probably won't cover in the class.
I have a question about the context point that you discussed. So how would that be a problem if you already give the reference translation?
Oh, yeah, that's not a problem potentially if you have the reference translation and you can make full sense of that reference. But oftentimes you may not have a reference and you might just have like a bilingual speaker who has to do the translation and then compare it to the machine output. So in that case, maybe it's hard to do this translation. Sorry, what did you say? Yeah, you could do that, but it depends on the scale of that you want this evaluation to be at. Maybe for your language, there's not that much labeled data, and collecting more would be somehow more expensive than hiring some bilingual speaker to make these judgments without a reference. I don't know, but yeah, I mean this is not a major issue compared to the other things that we discussed. Yeah.
So like during training, we use maximum log likelihood estimator generally as a function.
Yeah, we talked about how to train these models, right? You have labeled training data, parallel data in this case. You have some English text and French text that are, usually the European Parliament proceedings have lots of translations in different languages. This is a very common data set to train on, or like movie subtitles that have been translated into many languages. So yeah, you can set up the training objective just as a language model that we've seen earlier in this class.
Yeah, but during evaluation, we are using entirely different code. So is there any way to reflect that during the training?
Yeah, there is. So there's a lot of work on using reinforcement learning to kind of fine-tune these models using a signal from either automatic metrics such as BLEURT, or I'm not so sure how much work there is in using human evaluation scores to do this, but yeah, like I said, we're not going to get into that in this class, but you should read about it if you're interested. There's a lot of papers that try to do this, and none of them have been particularly successful. This is the takeaway. Okay, so we discussed a lot of motivations for why we might want automatic evaluation. They're easy to scale, they don't cost that much, I can do them on a ton of data instantly, and they're consistent, right? Depending on how I set up my automatic metric, I'm going to get the same score every time, unlike with humans where there might be this element of subjectivity involved. So the downside is that these automatic metrics are much less expressive. It's also unclear how much exactly they correlate to the human translation scores, although we'll talk about that later. Okay, so one very simple way of evaluating a machine translation output is, given a reference, just compute the precision and recall of the words that are produced by the machine translation system compared to this reference. So here I have system A. It produced Israeli officials' responsibility of airport safety. So of course this is not very fluent, but it generally has some words that also occur in the reference, right? Israeli officials are responsible for airport security. And so the precision here will compute what percentage of the words that were generated by the system appeared in the reference translation, right? So here I have 6 words in my system output. 3 of them, these green ones, appeared in the reference. So my precision is 50%. The recall is what percentage of the words in the reference appeared in the system's output. So it's like the inverse, right? So here I have 7 words in my reference, and 3 of them appear in the system output. So my recall is 3 out of 7. I can of course compute an F score to take both of these into consideration. So of course this has a lot of issues. One is it doesn't penalize reordering of these words at all, right? So if system A produced Israeli officials' responsibility of airport safety, system B produced airport security, period, Israeli officials are responsible. System B has all the same words as the reference here, and it gets 100% on precision and recall, despite being a bad translation, right? No one would say, if you gave this to a human, the fluency would be like 1 out of 5 probably. But using precision and recall at the word level gives you inflated scores. So we might want something that considers word order. That's definitely a basic property of this kind of language. And the BLEURT is just a very simple tweak on top of precision, word level precision. So to solve this issue, or to address this issue of word order, the BLEURT will just consider n-grams as well. So remember we talked about n-gram models, right? It's just a contiguous sequence of words. So for example here, Israeli officials' responsibility of airport safety. If I look at all bigrams, I would have Israeli officials as one bigram, officials' responsibility of airport safety, all of these bigrams, and I would just compute the precision of them compared to my reference. In the BLEURT, we use n-grams from size 1 to 4. So the maximum phrase length we're considering when computing the precision is 4. So the full equation for the BLEURT is here. We'll talk about this brevity penalty in a bit. But basically, there's a penalty that penalizes a translation for being too short. And this is, in effect, trying to model the recall in this equation as well. In the next few slides, we'll get to why explicitly putting the recall into the score is not a good idea for machine translation. But yeah, we're basically taking geometric mean of the precisions at all of these n-gram lengths from 1 to 4. So very straightforward. And in machine translation, in some cases, we will have multiple reference translations. So I could have the same sentence translated by 5 different expert translators. They all produce a slightly different version or a paraphrase. My metric should be able to benefit from having more references. In the BLEURT, by using this precision-based thing, it is very easy to extend it to multiple references. All you say is, well, an n-gram counts as a match if it occurs in any of the references. So as an example here, I have these 4 references, and my system produced the same thing, Israeli officials' responsibility of airport safety. So let's take a look at just the bigram matches in this system output. Israeli officials is the first bigram that appears. Now I want to compute the precision. I'm going to just look for every single reference. Is there any of them that uses this phrase, Israeli officials? And of course, in this first one, we see that it's used. So we get a match here. And if you look at this phrase, responsibility of, we'll see that it doesn't occur in the first reference or the second reference, but it occurs in the third reference. And so I get points for this. Even though it didn't occur in the first reference, I'm using the multiple references to, so all possible bigrams that are in any reference counts as a match for my, my score here. Okay, so let's go through an example maybe with both of our system outputs from the previous case. So remember that at the word level, this translation, airport security Israeli officials are responsible, was getting 100% word level and precision and recall. So here we see that the unigram precision is 6 out of 6 on system B. We already saw this. If we look at the 4-gram precision, system A has no matching 4-grams. That's a 4-word phrase compared to the reference. System B has 1 4-gram. Israeli officials are responsible, which matches with the reference. So it gets some points for this, but note that there are 3 different 4-grams in this system output, and only one of them match. So it gets 1/3 precision at the 4-gram level. So here, system B is still scoring higher than system A, which we probably want at the end of the day, because this phrase, Israeli officials are responsible, is pretty, I mean, it's not a, it's partially correct. It's just kind of out of order. But it's not getting 100% now like it was in the word and phrase level metric. So you can see that including these larger phrases has reduced the score. The model no longer thinks this is a perfect translation of the reference. All right, so that brings us to this question: why does the BLEURT not account for recall? Maybe it'll be more clear if we go to this slide. Any ideas? Yeah.
We can just put the word not, and still the recall will be very high.
Sorry, say that again.
We can put the word like Israeli officials are not responsible for it, and recall would be very high. And the sentence.
Why would the recall be high in that case?
Because it has.
Oh, I see what you're saying. But this is an issue with the precision as well, right? So I'm specifically, you know, the BLEURT here, you can see that the only, it only considers precision of these n-grams. It doesn't consider the recall. Why might that be the case? Yeah, exactly. So there are multiple references in some cases, right? And if I consider the recall, that would mean that I'm asking my system to produce n-grams that occur in every single reference translation, right? Which is not possible. That would not, like, it would be very hard for a system to score high on this. So yeah, that's why instead of recall, we have this brevity penalty to make the translation, like, penalize it if it's too short. So if it's too short, it's probably dropping some important information that is in even a single reference. But other than that, we don't force the model to produce every possible phrase that's in any reference. Okay, so that's BLEURT. Is very simple. It's just a word level metric. Of course, it depends on tokenization as well, right? Like, what do you consider as a word? What do you consider as a phrase? We had this whole lecture on tokenization. In general, if you're computing the BLEURT and trying to compare it to a number that's in a paper or something, you need to be very careful that you are using the exact same tokenization as this other system, or your numbers could be wildly different. So that's something to consider. All right, so some of the drawbacks of BLEURT. Of course, one is that all words and phrases are treated as equally important in this computation, right? So if we go back here, Israeli officials and responsibility of are treated as equally important, although possibly we might want the first one to be more important than the second one. And the way in which BLEURT handles word order is simply just to extend the precision computation to include slightly longer phrases, right? Up to 4 words. But this is not solving the problem completely, right? It's just making it a little bit better. It's still a very local score. As we saw with this translation getting a fairly high BLEU score, despite a human would not say that this is, you know, a remotely good translation. Finally, human translations score low on BLEU. So this is, you know, of course, interesting point, because if you have a real human translating a sentence, you would hope that your automatic metric scores the human translations higher than a machine translation. In general, this is true, but the magnitude of that difference is not what you think. Like no one is getting a BLEU score of 100. No human translator is getting the max BLEU score. So the upper bound is kind of misleading. Okay, there's a question, how to account for synonymous words. Yeah, so using multiple references is one way to do this, but we'll talk about other ways later on in this lecture that do a better job of that. All right, any questions so far? Yes? That's a good segue into this slide. So despite all of these flaws, there's still a correlation between the BLEU score and these judgments of things like adequacy and fluency that we get from human evaluators. So while the absolute upper bound of the BLEU score is not 100, the number does seem to correlate. Like if you have a translation system that gets a low BLEU score, it's also likely to have low adequacy and fluency scores as measured by human experts. So this plot shows this correlation. This is showing the NIST score here, which is some kind of variant of BLEU, but very similar. And you see that there's a correlation here between the human judgment score and the automatic metric score. So as long as there's some correlation between these things, it means that the metric is probably useful for developing models and judging which model is better than another. And the BLEU score has been and is still widely used in translation literature. Like if you, even now in 2021, write a paper on machine translation and you don't report the BLEU score, it's probably not going to be accepted because people expect this score to be in it. So yeah, that's the reason. Yes, so we'll get to this in, this has only recently been happening, and it has actually been difficult for people to come up with such a model that is better, like has higher correlation than the BLEU score, but now it has happened. So we'll talk about some of those recent developments soon. Other questions? Okay. So before we switch to those more interesting models, I just wanted to mention another metric which you've probably seen when reading some of these papers on text generation, and that's the ROUGE score. It's very similar to BLEU, except there's no brevity penalty, and we're looking at the recall instead of the precision. So the high-level idea is, let's just look at what percentage of the words or n-grams in the reference occur in the generated output. So this score is used to evaluate summarization systems. This is its most common application. And so one natural question is, why do we use this recall-based approach to evaluate summarization but not translation? Any ideas? So in summarization, remember that your input is maybe some massive news article or a collection of articles, and your output could be a paragraph that summarizes all the important information that is in those articles. Yeah.
By design, we're trying to use less words for this task, so not to get a lower precision from the.
Well, remember that precision is based on the generated words, right? So one way I could game this, like you say, is I could just have a model that copies the input completely, right? And so in this case, I would have very high precision. if it's an extractive summarization model. But I would not have accomplished the goal, as you said, of making an output that's shorter than the input that I got, right? So that is one of the primary reasons, right? Focusing on precision doesn't account for this main goal of summarization, which is to have something that's shorter than the thing that you're trying to summarize, right? Another reason is because in summarization, the output is already a collection of the most important things about the input. And so dropping any of those things is a giant red flag, right, for our system. If it missed some important thing that was in the reference summary, then we need to know about that because you know, a summarization should be producing all of the things that occur in the reference translation. So this is why in summarization we prioritize these recall-based metrics, and ROUGE is the most popular one. So ROUGE has different variants, like ROUGE 2, for example, is a bigram level a recall metric, very similar to the stuff we've seen with BLEU. But yeah, these two metrics, BLEU and ROUGE, are these word and phrase-based evaluations that, of course, they're very, very simple to use. That's their main appeal, right? They just involve counting word overlaps and phrase overlaps, and you can efficiently evaluate them on as much text as you want. So they've really driven the development of these translation and summarization systems, despite their flaws, for the last how many ever years.
Does this mean recall is defined a bit differently here, since we are only focusing on the most relevant words which make it to the summary, or are we taking a look at recall with respect to the entire text?
So in the task of summarization, your reference is a summary that someone has already written. So yeah. Other questions? Yes. Oh, that's a good question. So the question is, in summarization tasks, do we have access to multiple summaries of the same article? In general, no. It's very expensive even to get one summary, right? So common sources of data for summarization systems are, for example, like websites associated with news articles, like CNN, for example, publish an article, and then they have these bullet points that are like the takeaways of that article. And so one of the popular summarization data sets is just derived from crawling CNN and the Daily Mail for these bullet point summaries of news articles. And you can create a data set out of this. But you know, it's hard to get multiple versions of these bullet points for a single article. In general, it's very difficult to get multiple outputs for this task.
You said we don't want the model to output the entire text, but how will recall help? Because suppose if it does output the entire text, it will obviously have almost all the words in the summary.
Right.
In the reference summary, and then the recall will be very high.
Yeah, that's true. What did I mean by saying that? Whoa, there's... You can have a word limit on the summary? I mean, these systems are generally trained, like in that bullet point example I mentioned, they'll be trained to produce the ground truth summary. So if they roughly see that each summary is like 4 bullet points long, if you're training by maximum likelihood, the model will learn to output this end of sequence token after 4 sentences. So usually the length is not an issue during training. Yeah, I'll have to think more. I probably said something wrong. All right. Okay, any other questions? Yeah. From the reference sentences. Yeah. I mean, in the case of the CNN, Daily Mail, the bullet points do not occur in the actual article. They're separate summarization systems. Okay, so we have some questions. When we do abstractive summarization, summary can be thought of as an approximated distribution. Would using KL divergence be a good metric in this case? So remember that your system is producing a discrete sequence of text, right? Like you go through the sampling process. In general, you want a summarization, sorry, you want an evaluation metric that acts on two pieces of text. That's like the best type of evaluation that you can get. So I'm not sure exactly how you would be using the KL divergence in this case. But maybe it's something more similar to the types of learn metrics that we'll look at later on. Okay, so back to what you were saying before, there is a way in which we can do better than these kind of word or phrase level evaluations. And that is by taking advantage of all of the huge language models that we have nowadays, where we can go beyond just simple string matching, essentially, which is what these other approaches are doing. So one approach, which was among the first to come out in this space, is called Blurt. So very creative, BLEU plus BERT. And it was intended for use in translation evaluation. So basically, they took a pre-trained BERT model and they fine-tuned it on a variety of weird, like synthetic tasks that they made up with perturbed data. So for example, I could take a sentence and then shuffle it around, and then like I could shuffle some of the words and phrases. I could compute the BLEU score of that pair, like the original and the noised pair, and then fine-tune my BERT model to predict the BLEU score given all these various noised objectives. I can fine-tune it to predict RougeScore or all sorts of other things. So basically, this is trying to get a BERT model that is capable of handling these kinds of regression type tasks. Because at the end, what I want is to fine-tune my BERT model on supervised judgments that I get from humans. So for example, human scores of adequacy or fluency. If I can take a BERT model, it takes as input some reference sentence, some ground truth translation, some reference sentence and some machine-generated translation, and it can produce the number, like 3.4, of the adequacy score that a human would have produced. That's really good, right? Because then I can cut the human out of this equation and just use my BERT model as a replacement. Does that make sense? So like this first bullet here is just trying to get a pre-trained, getting a regression task into the pre-training objective of BERT. So you're basically first going to fine-tune it on these different synthetic regression tasks and then fine-tune it on a small data set of human judgments, because you don't have large human judgment data sets available. It's very expensive to get these. Okay, so the metric that now, as of like a few months ago, someone wrote a paper that said this metric, Comet, has higher correlation across a bunch of different language pairs and model settings and so on with humans than BLEU score. So there's no point in only reporting BLEU score. Now we should report this Comet metric. It's actually very straightforward. They have two different setups. This is taken from their paper published last year. We can look at the one on the left, which I think is a nice, simple example. So here you have a pre-trained encoder. This could be something like BERT or a multilingual language model like we'll see in the next class. We've already seen one such example with the byte T5, for example, right? That took in arbitrary languages as input and was able to do language modeling. Anyway, we have some pre-trained encoder like a BERT. The inputs to this model are a concatenation of the hypothesis. So this is the thing that is generated by the machine translation system. Then the source sentence, so this could be in a different language, right? And the reference, which is the human written reference. So I have all three of these as input to my, my model, and I pass it through BERT. So at the end of this, I'll get a token level vector representation for each of the tokens in all three of these sentences. And what they do is apply a simple pooling operation. So this could, I think in their case, they just average the vectors together to get a single vector. I think probably for each hypothesis source and reference, they get a separate vector by averaging those tokens together. Then they concatenate those, put them through a feed-forward layer, and then they're training this as a regression problem. So given this final vector, can you predict the number from 1 to 5 of what a human thought was the adequacy of this translation or the fluency, right? So they're using the mean squared error, the square loss, as we saw when we were talking about backpropagation, because this is now predicting continuous values here. Although you could also treat this as a classification problem with like 5 different labels, but here they treat it as a regression. So on the right-hand side, we see a different setup of this comment model, which is a ranking-based model. So here they have the source and reference like before, but now they also have additional data on multiple translations produced by a system, and humans have judged whether that one of them is better than another. And so this kind of data is much easier to collect than judging from 1 to 5. Here, I mean, it's not easier, but it's conceptually an easier task for your raters, right? If you just say, here's sentence A, here's sentence B, which one is better, right? You get this binary judgment. And people can do this in generation evaluation as well. And can we use this kind of data to further improve this kind of evaluation? So here I have one system output that humans said was ranked better than the second system output, this worse hypothesis in this slide. So we take the same setup. We have this pre-trained encoder. We pool, we get these sentence embeddings, but then instead of concatenating them and feeding them through a feed-forward layer, here we're going to use a contrastive loss function, like a max margin loss, to make the better system outputs representation closer to the correct, to the reference, and farther away from the worse the worse system output. So you don't have to understand the details. If you're interested in this, you should read this comment paper, but they basically released a library on GitHub where you can just put in your model's hypothesis and the reference text. And also this one needs the source text as well. So note that in BLEU, you only needed reference text. But here, you actually are using the source text. This is also helping make this a better evaluation metric. And this thing overall has higher correlation to human judgments than BLEURT alone. So it's a nice new development in evaluation of translation systems.
Since this is already being told, so is this somehow a machine translation model in itself?
But it's not actually producing a translation, right? So it is using the source text, but not to produce a translation, probably in some more coarse grain matching type of thing. Again, it's kind of hard to explain what exactly it's doing, because at the end of the day, in this case, it's just predicting a number, and they probably found that including the source makes the correlation to human scores go up. And so maybe it is doing some coarse grain matching of, like the base pre-trained encoder, if you're using something like byte T5, it already has some rudimentary understanding of all of these different languages, so in the same embedding space, right? So possibly it's very easy to compare between phrases that are in different languages with these kinds of pre-trained encoders. But yeah, for the encoder, it's very important to use a multilingual language model, which is what we'll talk about on Wednesday. So if you're confused now, hopefully you'll be less confused then. Yeah.
Should we use both of these models or one after?
That's a good question. I think they, for many tasks, prefer to use this ranking-based one because it does take some extra information into account with these two hypotheses. You could also use both of them potentially. If you have this model and then fine-tune it with this loss as well, then you might do better. But I think the results in their paper are primarily with the second model. All right, but I mean, it really depends on the language pair, right? For some language pairs, you might not have this worse, these two hypotheses ranked, and so you probably can't fine-tune this kind of model. So you can use this other one. Yeah.
So if you remove, say, the source in the order,
Yeah.
how is it different from a sentence similarity model? Different or not?
Well, the difference is just in the data, right? So here I have fine-tuning data that's provided by these expert translators or annotators on how similar or how adequate or fluent is this hypothesis compared to this reference, and they did that that scoring with access to the source sentence as well. So yeah, I agree that if you remove the source, then it becomes very much like a sentence similarity task, although you also wanted to judge fluency as well, so perhaps that's a little different. In this BLEURT paper, I believe they didn't use the source text there, so it's very similar to what you're saying. But yeah, if you care only about adequacy, then perhaps you can do very well already without including the although, I guess that's also true for fluency. Fluency you can do without any reference at all, so, yeah. All right, so the last part here is going to move away from automatic metrics, which we've talked about several types now, but they're all very limited inherently, right? Even like these BERT-based ones or these pre-trained encoder ones, we know that this pre-trained encoder is not understanding language at a human level. So its judgments about language will always be limited in that aspect. So these slides come from a project that my postdoc did, Marjana, where we were evaluating open-ended text generation. So this is a very different problem than translation or summarization, which are more constrained, right? Even if there's multiple references, they're usually all paraphrases of each other. In a case like this is from Reddit. There's a subreddit called Writing Prompts where someone posts a prompt like, "You, a video game character, just died. You had no spare lives left." And you know, like a bunch of different users write their own stories based on this prompt. So of course I can write many different stories given any prompt, right? I could probably write infinite stories that are inspired by this prompt. So it makes the concept of having a reference kind of weird, right? Because this reference is relevant to this prompt for sure, but it still makes it very difficult for me to evaluate a system output given just one reference, because I have one story out of infinite plausible stories. What does it mean to compute RougeScore or BLEURT with this kind of setup? It doesn't mean anything, really. So here, there are no automatic metrics that are particularly useful. And so we need to resort to human evaluation. And human evaluation, as we mentioned with the translation case, has these time and financial constraints. It's hard to scale up. People for these kinds of tasks commonly use crowdsourcing platforms like Mechanical Turk, Amazon Mechanical Turk, for example. How many of you are familiar with Mechanical Turk? Okay, about half of you. So basically, it's a platform in which anyone can post a job. So say, if I were doing this task, I could post a job to Amazon Mechanical Turk saying, "Look, I have all these machine-generated stories. I want you to rate them from 1 to 5 on how good they are," or something like that. And Amazon Mechanical Turk also has a bunch of workers. It has, like tens of thousands of workers who will perform these tasks in exchange for payment. So you could say, I'll pay 10 cents per judgment. And because you have access to this huge crowd of workers, your evaluation tasks get done a lot sooner than they would if you actually hired some expert, English teachers or something to grade these stories. So the crowd can be a good source of, labor. It can be very efficient to evaluate these systems, even if you're doing human evaluation. But as we'll see, it also has a lot of downsides. But okay, so this is a task, story generation. There are many other text generation tasks that are open-ended. So for example, question answering can be viewed as a generative task in which I might have a question like, why is the sky blue? And I might want a model to generate an answer to this question, right? So generate some text. But here, there are many different ways to explain why the sky is blue, right? So we run into the same sort of problem where stuff like BLEU and ROUGE are just not useful in these kinds of scenarios. So, other tasks that people are looking at, like simile generation or other sorts of creative language tasks, none of these automatic metrics are meaningful in these cases. And now that we have these huge language models, right, it becomes increasingly important to focus on these other tasks that are now possible that weren't possible before. So these days, we see a lot of people who are making models for various tasks that have never been automated before. You might see something like AI Dungeon, for example, which has a language model backend. And it's really hard to evaluate the outputs of a model in these scenarios without actual human feedback, right? So in cases like AI Dungeon, I can deploy my model to real users and solicit their feedback, right? Maybe this output from the model just completely broke the game or something, right? But in most settings, it's really hard to get access to people who are invested in the task that you're working on. Okay, so anyway, in this kind of story generation experiment, we have these prompts and stories like we mentioned before, and let's say that we also have some model that we want to evaluate. So in our case, we looked at GPT-2, which is one of these OpenAI's language models, not the biggest one, but it's a pretty reasonable one. So GPT-2 generates all of these continuations of this prompt. So one question is, here I have these like 3 different continuations. If I'm given just a single prompt and I have this language model, how can I generate multiple continuations that are all different from this language model? Yeah, so I would use one of those sampling-based decoding methods, right? So given the same prompt, I could use nucleus sampling or top K sampling to generate 100 different samples, and each of these would probably correspond to 100 different stories. Although, GPT-2 does not generate particularly good stories or coherent stories at times, but I would get 100 different outputs. So anyway, here for each prompt, we've just taken one sample. And one of the things that we can evaluate, similar to adequacy and fluency, is a couple of properties on a scale from 1 to 5. So we looked at, and these are common properties that people care about regardless of what task that they're evaluating. So grammar is related to fluency, right? What is the grammatical correctness of this input? Coherence is important when you have multiple sentences that are being generated by your model. So how well do these sentences fit together? Are they logically ordered properly, and so on? Likability is probably the worst thing that you could ask someone to evaluate because it's extremely subjective, right? I could read this story and be like, I don't like Zelda, so this is not enjoyable. Or I could be like, I'm a huge fan, this is enjoyable regardless of whether it makes sense or not. So we added this in our experiment because almost every paper we looked at in this space evaluates something like likability, but in general, there's no agreement. You probably shouldn't evaluate this, even though this is probably the thing that you care most about, right? If you are making a story generation system, you want it to produce enjoyable stories. It's just very hard to have a meaningful evaluation of how much someone liked some sort of story. Okay, and then relevance is very important, right? So I can have a perfectly grammatical, coherent, and enjoyable story, but it needs to also be relevant to the prompt that I gave this language model, right? So these 4 properties, we asked people on Amazon Mechanical Turk to rate from 1 to 5, where 1 is the lowest and 5 is the highest. Okay, so one thing that we found here, and we don't have to look too much at this table, but we we had the Amazon workers rate the reference text. So we had like some subset of workers rate the reference text. So these are stories that are actually written by Reddit users and got a lot of upvotes, so people like them. And then we had another subset of workers rate the machine-generated stories, which are clearly worse. Like, they're not good stories. The problem with Mechanical Turk is that these workers can't really distinguish between the machine-generated stories and the human-written stories. If you look at grammar, well, the grammar of the language model is pretty good, so we can skip that. But coherence, they gave the reference stories, so we had 3 different days on which we evaluated the reference stories, roughly a 4 out of 5, so pretty good. But the GPT-2 generated stories were also around 4 out of 5, even though they are not coherent. I can tell you from reading so many of them that they're really bad. The relevance was also just slightly lower than that of the references, and the likability was, roughly the same. So these workers, granted, likability is not a great metric, but they liked the machine-generated stories about as much as they liked the human references. So we saw these results, and we were a little confused because from reading these stories carefully, it is very clear that machine-generated text is not as good, not anywhere near as good as human-written text. And then we started looking more at the Mechanical Turkers who are actually rating our stories. And we wanted to see how long they're spending on reading these stories. And the median time was 13 seconds. So if you imagine getting 150 words, every one of these stories was 150 words. It's impossible to read that carefully in 13 seconds. Like, we did some experiments ourselves, and it took like a minute on average to read one of these stories, and read them in such a way that you can rate all of these properties is very difficult. So we concluded that many of these workers are not doing the task at all. They're just, clicking random things, and then, we're looking at that data like it's meaningful, but it's actually not. So this is the price you pay for having access to a huge crowd of people, and paying, not that much to get these annotations. Is that, if you're not paying them like reasonable wages, and we were paying them minimum wage in the state of Massachusetts, but still, they're going to pick tasks where they get the most money in the least amount of time, right? That's rational for them to do. And if you don't have any controls on your task to, for example, prevent them from submitting something until a minute has passed by or something like that, then they're going to do, on average, what you don't want them to do and just spam your task, essentially. So especially with subjective tasks like this, it's hard to weed out people who are not doing the task properly. So if you are ever in a case where you're using Amazon Mechanical Turk, just be very aware that you need to have a very detailed validation pipeline to filter out all of these bad workers. And in general, you can do your best, but after some point, it's difficult to use untrained people to perform some of these tasks that require a lot of reading and so on. So just to wrap up, we also compared the Amazon Mechanical Turker ratings to certified English teachers ratings. So we actually got some English teachers to essentially grade these stories themselves. And they had no problem figuring out that the human-written stories were significantly better than the machine-generated stories. So of course, this is more expensive for us. And it's hard to find English teachers, right? So these are definitely obstacles preventing you from evaluating your text with experts. But at the same time, if you use Amazon Mechanical Turk, you're going to get a very misleading representation of how well your model is doing, right? Some people might look at this table and say, wow, your machine is better than humans or something like that at writing stories, right? And some news article will come up about that and hype everything up, but that's not true. So then the most interesting part about this is the discussion with these teachers afterwards. And one thing that all of them mentioned was that if you just show someone a scale from 1 to 5 and say, rate this property of the story, they have no idea what the ends of the scale mean, right? And one problem with the setup here is that the scales, the definition of what is a 1 and 5, differ depending on what kind of data you're showing them. So GPT-2, for example, makes a whole lot of coherence errors compared to a reference text. But if all of the data you're seeing has, on average, some number of coherence errors, then you're probably going to assign the average to a score of 3. Whereas with a human reference, which doesn't have these issues, seeing even one error like this might be enough to shift you all the way to giving it a 1 out of 5, right? So this issue of calibration is severe when you're comparing two different models with different output distributions. You need to train the workers in the task that they're trying to solve. So you need to show them, say, 10 examples from the model that you're evaluating before you actually start collecting judgments from them. So another thing that they said was that reading the machine-generated text was much harder than reading human text because of all these errors. And we could see that in the time it took them to read these stories. So when reading human references, they were taking about 70 seconds per story. When reading machine-generated text, it took them about 90 seconds. So there's clearly some cognitive load associated with reading these messed up machine-generated stories. And one other thing that we concluded was that in these cases, if you have a reference, you should always pair up the evaluation. So if you have a model-generated output, you should show it alongside the reference text to the workers so that they can do a better job of calibrating their results. So what that means in this case is if you have a reference story and you have a model-generated story, they're generated from the same prompt, then show them side by side and then ask the worker to evaluate like the machine-generated story or something like that. All right, so I think that's all I had. Basically, the takeaway is that evaluation is not solved at all. We have these simple metrics like BLEURT and RougeScore, but they have very obvious limitations. We have recently moved forward to these more language model, neural language model dependent scores like Blurt and Comet. But for many generation tasks, none of these metrics are useful, and we have to do human evaluation. That has its own challenges. Evaluating text generation models is a very open field at the moment, so lots of interesting papers coming up these days. All right, so on Wednesday, if there are no questions, then we can talk about the, okay, there's one question. Go ahead.
You mentioned that we did this.
I'll post on Piazza, the paper link. It's one of our new papers at NLP this year. All right, so next time we'll talk about multilingual language models, talking about not only translation, but a bunch of other multilingual tasks that can be done now that we have these multilingual language models. So see you then.